Why don't you have indices there? In G?
Because I don't know which one to do.
Sorry?
Because I don't know which I should use here.
It has to be a scalar. And it has to be contracted with delta G. Yes. And what is a delta G? And if you write it, then it should be the other contraction.
So that now means
Should I put whatever then?
I don't know, like those. Okay. Change those.
The metric can write the index of the second F.
So what is this G? You are copying it from the upper line.
Yes. So it's this.
So what is it doing? It's contracting two of the indices of F.
It should be nu and beta.
Yeah.
So you should do the same thing.
Yes.
Doesn't matter what you call them, it matters
Where
What it does.
what it
contracted.
contracts.
Yeah. So here I have G. This is contraction.
Wait, you made a mistake here.
What?
Because you're calling it mu and alpha there to contract it with the first two terms. So you have to relabel the indices in the second term.
Here.
No, the second term, yes.
This one. Or
I mean, check the contracted indices and name them together.
You want to use
alpha, sigma.
that one, you have to rename the first term.
I mean, you're taking delta G mu alpha, right? Outside from the first term.
Mm-hmm.
And then check the contracted indices in the second term and then name them to be mu and alpha.
But he's using
lambda
nu from the term.
Okay, let me finish it because we only have 15 minutes. But thank you.
Do you get my point? That is, you're taking it out. So just contract it with the second term. The things that are contracted.
So here we have
the rest,
mu
the mu indices.
alpha as free indices.
Yes, so it should be.
So this will be mu alpha.
And then contract it with this
And
term.
then in this term,
Check
this was just
F squared.
square.
You don't need to care about that.
and we need free indices.
Yes.
Mu alpha, and let's call this
Beta. Yes.
and this is just G mu alpha.
Yes.
So what do we get at the end of the day? We get T mu nu equals 2 over square root of G delta S delta G mu nu. And that is going to be minus 1 over 2 F mu alpha F mu alpha. Sorry, there was another 2, so there is 1 over 2 minus this plus 1 over 4 G mu nu F squared. Okay, so does it matter to keep a mu with lower index fixed or a mu with upper index?
With lower index.
It doesn't depend on how you vary. You vary with lower indices.
You have to fix lower index.
Say?
Okay, this is how I thought about it. If you vary G mu nu with upper indices, you have to fix A
with the lower indices and vice versa.
Why?
Because in here in the action we lower the indices by adding the G mu nu with upper indices, and we vary with respect to those. And if you want to rise the indices, you have to multiply by G mu nu with lower indices, and you have to vary with them.
No.
This is how it works.
I think we proved it. I mean, Alejandro proved it that the connections cancel with the indices down. Mu nu. So that is the only way to do it. Because
No, imagine if we had connection, couldn't we do variation of the connection with respect to metric? Connections are also functions of the matrix.
Metric, yes.
Also, metric with lower index and upper index are not independent.
Yes.
So you can, like here for instance, we have a square root of g, and it was written in terms, you can write it both, you can write the variation on this in terms of both,
Yes.
because they are not independent. So what is the rule? What is the rule?
With lower index.
Why? Did you try doing it with upper indices? What if you wanted to do it with upper indices? Let me try to do it with upper indices. So we have S of the S as a function of metric and A. Let's say it doesn't matter if I put lower index or upper index, because these two are not independent. One of them is inverse of the other. So now let's say that I want to take the action to be functional of G mu nu with upper index. G mu nu, it doesn't matter. A mu with upper index. So I want to take delta S, delta G mu nu, keeping fixed a mu with upper index. We want to ask what is this, and then we multiply by that 2 over square root of g. So what can I do? I can do a trick. The trick is the following: S a mu with upper index is S of the same G mu nu and G mu alpha A alpha. Right? Now I can or let's actually do in fact I want to do another thing. So now you can think of it as S of G and A alpha with lower index, right? Because now it's a function of the metric and A with lower index. So I can write this object as delta S, delta G mu nu with A alpha with lower index kept fixed, plus the variation of the action with respect to say alpha, and then delta A alpha, delta G mu nu with upper index. This is the variation of the action when I keep G fixed. Right? But A alpha with lower index is just G alpha beta times A beta. So let me see. Now here I want to fix A with upper index fixed. So do you understand the logic or not?
The first term is you're differentiating the second term?
Yes, I'm saying that if I consider this action written for A alpha with lower index, right? I can write it also in terms of A with upper index. So whenever in the action, for instance, in the action you have F mu nu, right? Which is d mu A mu minus d mu A mu. So this I can write as d mu of g mu alpha A alpha minus d mu of g mu alpha A alpha. Now I can ask what is the variation of this action with respect to metric. So we want to ask this question: what is delta d by dg mu nu when I keep a mu with upper index fixed, right? So the way to do it is to so delta of s, g and a with upper index. The way to do it is to take the variation of g and a with lower index. So say this in this term there was no g mu nu, so it was only f. I take the variation with respect to a mu with lower index, but remember that every a mu with lower index has a g mu nu in it. So that's what I'm doing. I'm saying that in this action, g mu nu comes from two places. One is, in fact, I think I should have written it like that. So let's take the original action, which was the function of metric and a with lower index. So you can write it as action as a function of g and g mu alpha, a alpha. Now, when you want to do variation with respect to g, keeping a mu fixed, you get variation with respect to g from two places. One is when you vary with respect to this metric, and one is the factors of g mu nu that come from here. So, one term is when you take a mu with lower index fixed and just vary with respect to metric. The other one is when you vary with respect to a with lower index. But remember that every a with lower index contains a factor of g.
Yes.
So there will be an extra term coming from here. So this is what we already calculated. If I put this 2 over square root of g, this first term gives me the t mu nu before. What about this term? Well, this is a variation of the a alpha. So a alpha is something like that. If I do the variation, what I get is going to be, since I'm varying g with lower index with respect to g with upper index, there will be a minus sign. And I will get a mu delta s delta a and then I will have g minus g mu alpha g mu beta a beta. And then this term can be written as just delta S, delta A mu. Or well, I can just keep it like this. Yeah, I agree with you.
How did you get this? Can you please explain?
How did I get this? This is just, I'm taking delta G alpha beta A beta delta G mu when A beta with upper index is kept fixed.
Okay.
Right? So A beta is with upper index is kept fixed, therefore this is just A beta delta G alpha beta delta G mu.
And that should be this, yes.
And this is going to be
Yes.
with the minus sign. Okay, now this term is just proportional to the equation of motion for A. Right, that's how we derive the equation of motion. We take variation with respect to phi. Therefore, T mu nu, the new T mu nu is the previous one plus something which is proportional to the equation of motion. And therefore, on shell, it's going to be the same as the previous one. So yes, you get different answers, but on the equations of motion, they are equivalent. Any questions about So there are 4 problems. Which one should I do? Any questions about the other? What is the energy of the Schwarzschild black hole? And
But that's with the lower index, right? That's with the lower index and the zero lower index. So, okay. I got P with the zero downstairs M. So, but usually the energy is P0 with the upper index.
well, we are calculating some quantity for asymptotically Minkowski spacetime.
Yes.
If it is asymptotically Minkowski,
Yeah.
the metric is
Minkowski.
yes.
Yeah, if I look, it's minus M.
Oh, so you're getting minus n.
If I change the,
Oh, okay, then there is a sign mistake.
that's what I'm asking. Is the energy the P0 with zero upstairs
Yes.
minus M or M or plus M?
Oh, yeah, I guess it depends a bit on the conventions, but I think we usually take the one with zero upstairs to be positive. Right? For like when we talk about U mu, it depends. It's not that crucial. Like whether it depends whether you define U mu to be 1V or minus 1V. If it is this, then I would say, yeah, I think, but it's a matter of convention. I think we usually define M to be like that. P to be M U mu.
Yeah, that's what I'm saying.
And therefore this is M gamma V. So this is positive.
Yes.
But it just means that your formula has a minus sign.
Very sure. I don't know. Because Julian got the same thing, the same sign that I got, but yeah, that's the same, the formula in the notes. Can you do that, probably?
Yeah.
Because Alan Guth was saying that we usually associate to gravity negative energy. So that's why I thought, oh, I got plus envelope with the lower index, so that's right.
Well, I guess what he was saying was a bit metaphoric. Don't take it too literal. Okay, so how do we calculate this? We know the metric, and we define this pseudo tensor of a stress energy tensor, and we said that we can define the concept for momentum, or in particular P0, as the integral d3x of the zeroth component of this. And then we said that this reduces to a boundary term. The dsi. So we express this tau in terms of some linear expression in h mu nu, which was anti-symmetry in the upper index, so the derivative of that, and then we use the Gauss's theorem to relate that to the boundary interval. So the final object was we reduce that to the area integral of this tensor, and this Okay, now I want to calculate this HI00, and that is given by, I'm just using the formula that we have. And then minus d0 hi0 minus delta I0 dj h0j minus delta 0 0 dj h beta beta. So here I have just considered this particular index structure of that general expression. But many of these terms are zero, like this is zero, this is zero, there is no time dependence, so this is zero. So what do we end up with? We have, and any I index can be lowered,
yes,
because we are in Minkowski now. Any zero index can be lowered with a minus sign. So this becomes di h00 plus dj hij 0 0 0. This one minus dj. Sorry, the indices now are screwed. So this is di. So here I lowered one in zero index, so this is minus, this is correct, this is minus di of h00 plus hii, which is minus di of minus h00 plus hii. This then is equal to that. Therefore, this cancel with that. What I get is dj of hij minus di. Oh, sorry.
It should be something else.
J is J. These are J. di of hj. So I get some expression that only depends on the spatial component. Now we can calculate. So do you agree so far? Now, given the metric, I can see how it looks like asymptotically. Right? So the metric is minus 1 minus RG over R dt squared plus dr squared 1 minus RG over R plus R squared d omega squared. Now I can write it in the Cartesian coordinates using the fact that dr, well, what is R squared? R squared is just xi squared, or xi. And if I vary this, then I get 2r dr is equal to 2xi dxi. Therefore, dr is equal to xi hat times dxi. So this is fact number 1. The second fact that I can use is that if I just take the delta ij dxi dxj, this is just the usual flat Euclidean metric. In radial coordinate, this is dr squared plus r squared d omega squared. Right? So now if I'm going to large distances, then Rg over R is much less than 1, then this metric is going to look like Rg over R dr squared plus dr squared plus R squared d omega squared. The spatial parts look like this. So this is just the flat Euclidean metric in Cartesian coordinate, and this term I can substitute from here. So the full, so this term becomes Rg over R x hat I x hat j dxi dxj. So now I can identify the variations of the method. So there is of course a d minus dt squared which combines with that and gives me the Minkowski matrix. So I want to write g mu nu as eta mu nu plus h mu nu. And if I want to write it in Cartesian coordinate, what I get is that h00 is equal to Rg over R, and hij is equal to Rg over R times x hat I, x hat I, x hat j. Where x hat, by x hat I mean xi over R. Okay, so then we need to calculate this combination, which only depends on hij. So it is dj of hij, which is dj of Rg xi xj divided by R cubed minus di of trace of that, which is just Rg over R. So this is this has a couple of terms. There is Rg over R cubed, then there will be delta ij times j, so xi plus x on that unit 3xi, and this x on this gives you minus 3. And from here I get plus Rg xi over Rp. So if I combine them together, I get 2Rg xi over Rq. Okay, so we should just plug this in there, and yeah, this gives me something positive, but I guess here I haven't been very careful of these signs, so I cannot answer your question about the sign because I mean, I can think there is a 1 over 16 pi g here.
Yeah.
But it's true that, yeah, this was what we call P0 with lower in there. It's very easy to fix the ambiguity, right? Because this pseudo tensor that we defined had some original expression. So remember, this was, or in general, this T mu nu was T mu nu of matter plus the nonlinear part of 1 over 8 pi g mu nu minus, maybe with the minus here, plus g mu nu linearized. Right? Now imagine you have so this object is quadratic in metric perturbation, because I'm already subtracting the linearized part. So this is quadratic in H. So consider non-relativistic system.
Okay.
Just a point particle, for instance. For point particle, we can fix our conventions for a point particle.
Okay.
That fixes the sign that should appear in this equation. Or in other words, you can ask if for a point particle, like what does this expression give you for a point particle? Is the sign that you get for Schwarzschild metric the opposite of that of a point particle or the same as that of the point particle? Right, that is the unambiguous question to ask, whether the mass for Schwarzschild metric is plus m in the same units in which, in the same notation in which the mass of a point particle is positive, or is the opposite. So my claim is that they are going to be the same. In the the conventions in which for a point particle you get positive energy, for Schwarzschild metric you also get positive energy.
So for a point particle, you have the T mu is momentum, two momentums divided by P0 squared, but with the upper zero.
Right, even there, depending on your convention, you can define it with minus that or that. So that's why I'm saying that it's easier to use to compare to these two things together rather than. Yeah, I'm trying to come up with the easiest way of fixing the sign.
But is it really that weird? Like, because wouldn't it change the Einstein equation if you can choose the signs? Wouldn't it change the sign of the curvature? Something completely scaling?
Yeah, if I change my definition of T mu and nu, I flip the sign of Einstein equation.
Wouldn't that change that wouldn't change the solution?
No, if I'm just changing my definition of T, I can just define T mu and nu to be minus 2 square root of G instead of plus. You can see both definitions in the literature. That doesn't mean much because it just means that whether T mu nu with like some component of T mu nu is going to be energy density or minus energy density, but
yeah.
Both signs can appear. It's just a matter of convention. It's nothing fundamental. But once you fix it, so that for normal matter you get positive energy, and you get the usual Newtonian potential that you expect for positive energy, then you can also ask this question there. Another thing is that the Schwarzschild metric is the metric that you get outside of a normal particle. Even if you have a very dilute star, outside a spherical symmetric distribution of matter, even if there is no, even if it's not a black hole, just some matter field.
Yes, that was my issue with the sign, because, for example, if I don't imagine there's a black hole, that I have a star that has collapsed, I would also have to account for the energy that is in the matter of the star, and not just in the geometry. Wouldn't that, if the geometry part is minus and the star part is plus, that would get 0 in total.
But this T mu nu is supposed to be the total energy. And as you see, it's the normal T mu nu plus something of order h squared. So imagine I'm considering some very non-relativistic system, a very dilute distribution of matter. Then this T mu nu is going to coincide with just the stress energy tensor of matter plus some small corrections of order v squared. So they are never going to cancel each other. So for a dilute distribution of matter, from this expression I should just get the normal energy that I would calculate in non-relativistic physics. You seem dubious.
No, okay.
I'm just saying that you can consider a system in which gravitational effects are negligible. And then the definition that I have for this pseudo-tensor coincides with the usual stress energy tensor. And then from there, everything that I did was just math. I didn't did any assumptions. So that also for that system, the result, you can follow this procedure and relate it to the field far away at infinity. Well, this field is basically the solution of the linearized equation in the presence of that matter density. So also for that you get Schwarzschild solution, except that you just linearize it, because before getting to the nonlinear regime you enter the matter field. So the gravitational radius is going to be much smaller than the size of the object. Before you get to the point that R G over R becomes order 1, you have entered the matter and then the solution changes. But outside you will get the same Schwarzschild solution. So this is the same solution that describes a very dilute non-relativistic star. And so on the one hand you can relate this expression to its weak gravitational field at large distances. On the other hand, in that case you can just do the integral of T mu nu and up to V squared corrections, you get the correct answer. So yeah, where were we? So we had this 1 over 16 pi g integral dsi times 2rg xi over r cube. This is equal to 1 over 16 pi g. This is a spherical symmetry. This is spherical symmetry. So from this integral, we get just the area 4 pi r squared times the field. So if you like, I can write the r squared and put x hat here. In the limit that r goes to infinity, so these r squares cancel. I get 8 pi rg divided by 16 pi g, and this is just n. Up to the sign. So in my sign convention, it's true that P0 in lower indices is going to be positive, but I think that means that even if you calculate the energy of some point particle, then it's going to be P0 in lower index, which is positive in this convention. Questions about other problems?
I have a question about the light one because we have to give the surface equation, the equation for the surface, because the only thing I was able to do was the projections on the axis. Like for example, in the TX axis, how the light looks. In the TY axis, how the light looks.
TY axis? What is TY axis? What
TY is plane, sorry, plane.
I wanted you to give me.
The thing in the middle.
So what is the definition of a surface? The definition, when you want to define a hypersurface, you give me an equation f of x mu equals to 0. That's the definition of surface. For instance, if you tell me x squared plus y squared plus z squared equals r squared, that's the definition of a sphere, to a sphere with radius r.
Yes,
that's what I wanted you to give me.
Yeah, I couldn't do that. I could only do the projections.
So that's easy. because this metric that I introduced here is actually flat. So ds squared is diagonal. So it's dt squared. There's no t component, and then there is 1 plus x squared over a squared dx squared plus 1 plus y squared over b squared dy squared 1 plus z squared over c squared dz squared.
In the line cone, ds is 0, and I can only solve that when I have cancelled one of the dy's or dx.
Well, yeah, if you want to do it by brute force, it's going to be complicated. But there is a, that's why this is a star problem, because there is a trick to do it. And the trick is to realize that this is actually a flat metric, which means that there is a new coordinate system which is going to look like and what is x tilde?
And we know
X
it's flat.
theta is x.
We're counting the implicit transformation.
Yeah, because there is a coordinate system that I'm going to tell you what it is, in which the metric globally looks like Minkowski metric. That's the definition of that flat space.
Yeah, the integral of that thing, right?
Yeah. So the x tilde dx is equal to the square root of 1 plus x squared over a squared. So that means that x tilde is what?
Yes, yes.
And then similar expressions for y tilde and z tilde. A goes to B, here A goes to C. And then the equations for a light cone, in this coordinate system we know what it is. The light cone that goes through the center is a cone which is defined by t squared minus x tilde x squared minus y tilde squared minus z tilde squared equals 0.
So every time that the coordinates don't mix in the metric, it's flat?
Yeah. Well, I could put any f of x here. And that's not the only case in which the metric is flat, but that's one special case.
Yeah, brute force doesn't work.
So you're happy with what is it? The spherical coordinates Did you do 6 and 7? So what is the relation between force, for instance? What is the relation between F mu and the Newtonian force that we use in the radial coordinate? Say Fr. What is Fr?
The smaller part is
This is the same. F theta
R F theta.
or F theta. So what happens is that in the Newtonian, when we write, usually we work in Newtonian dynamics, the components of force all have the same dimension. So even F theta is just a projection of force in the theta direction, but it has the same dimension as Fr. While when we define vectors, in relativity, so this is supposed to be a vector that has so we are talking about a 4 vector that is expanded in these coordinates. So or bases, the bases that we use in relativity are partial derivative. So when we work in the spherical coordinates, this is going to be well, there is ft, but ft is 0. So there is a fr, and then there will be f theta, d theta. And therefore the components, the theta component and r component of the force 4 vector are not going to have the same dimension. F theta has dimension different, well, Fr, the difference between the dimension of the two is a factor of R. So what we really do when we work in Newtonian physics is that we multiply and divide this by a factor of R. And then when we are projecting into theta direction, we are thinking of a basis which has a dimensional length, not theta. So then R of theta becomes what we call the Newton. Other questions? Okay, if there is no other question, I'll go to seminar. Next week I won't be around most of the time. I think Paola is going to do the last homework on Tuesday. But you can email me if you have the.
H, capital H small in this stuff.
Okay, you have to read it.
Can I?
Oh, sorry.
No problem.
I forgot.
No, I want to go to the
H.
Dr. Katrina.
point?
About I have to leave early in August, so I have to talk to her about it.
Well, it's not a deal. We will prepare.
I mean,
you
I have to
everything
send
else.
her an email or something last year.
Okay, can I leave early also? But I don't.
But you
have-
need a reason to leave early.
I'm
I mean,
sick.
I will.
I'm sick of this place.
No. I will do my thesis defense before.
Where?
Here, I mean.
Yes. But, okay, so what about the university?
Oh no.
Everything?
Everyone.
Everyone.
Almost.
Well,
It's okay. I can get.
Yes. You get the project.